some time to look at what algebra really is, physically speaking, when you're looking at actual things and objects and not just math theory. But it always strikes me that we could even do things with math that we can't even quite visualize, and vice versa. Some interesting things we take for granted that I'll mention first is how math in general, even though it's a complicated process, you're doing a lot of things in those processes. So you're really not doing a lot of things per se. You're really taking shortcuts and using a lot of information in small packets when we're writing. Kind of like a word is a symbol, math is a language to describe other things, and sometimes those things are very complex. So let's take a quick look at a times table. So if we have a times table, what we're really talking about is length and width. So if we're doing the times table of 3 times 1, 2, 3, 4, 5, 3 times 5, we're asking how many units of squares or bricks, let's say, would be in this shape when there are 3 rows of 5 or 5 columns of 3, and so we know that this is 3 times 5, or in building we'd call it a 3 by 5. And we know that it's going to create 15 little squares or bricks. So we want to consider, how long it would take if we actually are people walking around and we have bricks in, let's say we're in Egypt. Do we really want to count 1, 2, 3, 4, 5 and 1, 2, 3, 4, 5, 1, 2, 3, 4, 5? Do we want to walk around? Do we want to take that time? Do we want to judge that we're not going to make a mistake in counting? Because what if it's 50? 3 times 50. Do you really want to go up and down 50 rows and count them? And we learn these little shortcuts. 3 times 5 is 15, and you add the little 0. Or even 30. 30 times 50. So 30 times 50, there's going to be 1,500 little blocks or bricks. So if we get into the idea of math being actual physical things, it even could begin to be very fun and interesting. We can begin to talk about dimensions. And then we'll get back to how numbers are like bricks, and how x or a variable x or y are like rows of bricks. And squares, x squared, is actually talking about an actual square. So one thing we could look at is the pattern of dimensions in math. So the first thing is a point. And we say that a point has no real physical shape. It's pointing at something. Like when you point on a map, you're pointing at something. So the first dimension we would call a first dimensional shape, 1D, would be using 2 points to connect and make a straight line. So we want to ask, how many of the previous things did we use? So looking at this, we have 2 points, so the previous one is a point. We use 2 points to draw that line. The next object would be a two-dimensional object in math. So it would have a length, and then it would go off in right angles to those points. And it would be a square or a rectangle. So when we ask, well, how many of the lines did we use? How many of the previous one, which is a line? 1, 2, 3, 4. Okay, then we can go into the next shape. We call it a 3D shape. We have 3D glasses, and we try to represent 3D shapes. So we would have a box. And again, what we're really doing here is we're making right angles at each of those points, and then we're connecting all the vertices. So again, you're putting right angles to each of the previous shape's corners. So now let's ask, how many of these squares did we use to build this? And it's actually 6, because we'll have the top and the bottom, and then the front, the back, the left, and the right. So here's the top, here's the bottom if we unfold this box. And maybe this would be the front, this might be the back, this might be the left, this might be the right. So we can continue this pattern, but we couldn't represent it in actual shapes. We can imagine it, but we would get into a four-dimensional shape. So we could kind of describe it. It's going to be using 2, 4, 6. We follow the pattern. It'll be using 8 of the previous shapes. So it'll be a shape that starts with a cube, and wherever there is a point, a vertex here, 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 and here, we're going to branch out into right angles, and we're going to have 8 cubes making this 3D shape. And it's really not something we can draw. We can kind of imagine what it might look like, and that's what we call a tesseract. So if you go on to Google and search for tesseract, it's a four-dimensional shape representation. It folds into itself infinitely, and it's basically one cube in the middle, and there's 7 more cubes attached to it at each vertex. And we have to consider that this is a two-dimensional drawing trying to represent a four-dimensional shape, and it kind of looks 3D to us, but it's really not a four-dimensional shape. And they even mention this in the Avengers movie. So we can look at these dimensions, and mathematicians have said they can understand that there are 5D, 6D, all the way to the 11th dimension, and not including time, I don't think, because when you get into physics, time is another dimension. So this object, they might call it 4D because it's a 3D object in time, when it's really a real life thing. It's happening at a certain time in life. So we can continue the pattern, like the next 5D shape. 5D shape would have, kind of mind-blowing, there would be 10 tesseracts connected to make a 5D shape. So how would we represent these in algebra? Well, when we're talking about a row, a point is like a number. When we're talking about a row or a line, it's going to be like the variable x. When we're talking about a dimension with length and a width, it's going to be a square, and it's where we get x squared from. A cube has a length and a width and a height. It's one more dimension from the one before it, so it's x to the third. So x to the fourth, it's interesting because we can manipulate it. We can say it's x squared times x squared, but we can't really even imagine what the shape would be. Yet we could still use the math to calculate and solve things and graph things. So it's interesting, just sort of like in writing, you can sometimes imagine things with your writing that haven't been created in the world yet. And yet we can do the reverse. We can describe things that have been created in the world. So let's take this idea and talk more about what algebra might be if we're looking at it practically speaking. And so in Common Core, they use things called algebra tiles. I want us to pretend we're in Egypt and pretend we're builders. We're going to create a real practical use for each of these things. So each little square I'm going to consider like a brick. And each little block, we would have sometimes algebra tiles we use. Those would be like numbers. 1, 2, 3, 4, 5. Here there's 3. Okay, then we have a row of bricks. And we don't know how many little bricks are in there because in math sometimes we're working with things where you don't have a definite number. So we would call a row like the variable x. And then we would get 2 squares. So what if we wanted to build a row? Well, we would have to use, to build a square, we'd have to use rows. And so a square is actually talking about x squared. And we can go to the next one. If we really wanted to, we can build a cube. And so a cube is where we get x cubed. So a cube would have 3-dimensional space, and you would have a bunch of little cubes if you broke it up. You'd have a bunch of little mini cubes inside of there that would fit in that space. So in the algebra tiles, they even begin to multiply. They might say, okay, here's a row times 3. Well, wouldn't that give us 3 rows? And then they would sort of fill in the space. Yeah, one row, 2 rows, 3 rows. So 3 times x, the number 3 times x gives you 3x, 3 rows. Another way they might do this is a row of something times a row of something else. But again, we're using the same amount, so it could be a row of 4 and another row of 4. When we multiply it, we're going to have a square. So that's how we get x times x is x squared. So again, this would be like x, and this would be like x. X times x is x squared, or gives you an actual square. We could say 4. You could put a number in. If it's made out of 4 bricks, well, 4 rows of 4 is going to give us a square of a 4 by 4 square with 16 bricks. So practically speaking, we would use 1, 2, 3, 4, 5, 6 numbers of bricks. Then we would have rows of bricks, and we can have squares of bricks. So we can get into even what a perfect square is. But let's just look at how we would use this in algebra. So I want to say that I have a couple rows of something. Let's say 3 rows of some amount of bricks, but we don't know how many. And then we have 2 little bricks left over. And we know that we're using, make it an easy one, we're using 32 bricks. And you might be able to even do this in your head. Basic algebra we could do in our head. But the point is with algebra, understanding the theory, is that we can do very, very complicated things that you can't visualize in your head, and you may not be able to count. So what is this looking at, and what does this mean algebraically? This is actually saying 3x, 3 rows of something, plus 2 will give us 32. So let's kind of manipulate it and move it around the way we would do it in algebra. Well, we have 3 rows of something with 2 left over. If I take out the 2 left over, and then now I have 30. So what we do here is we subtract 2 on both sides. Now we have 30. And so if I asked you if you have 3 rows of something and you equal 30, you would probably be able to say, well, it must be rows of 10. 10 and 10 and 10 makes 30. And that's where we would here divide by 3 and get x equals 10. So imagine if it's a really, really big amount and we don't want to be able to do it in our head. Let's say we have 7 of them. And 3 left over. And so this isn't even that big. What if there's 350 rows? So we could do these. We would say 7x plus the 3 left over, here's 3, equals 213, let's say. So again, what we're really doing here is we're sort of manipulating actual moving, actual objects. So if I take away the 3 here, I gotta take away 3 from my total. So that's where we would say we subtract 3 on both sides, keeping it balanced. So 7 rows of something makes 210. We divide that by 7, we get 30. So rows of 30. 7 rows of 30 plus 3 left over will give us 210. So we're actually doing things that are useful for someone who is building something. And then we can translate this into almost anything, finance and building and art, numbers of crayons. I mean, algebra allows you to manipulate lots of different pieces of information. So what about squares? Well, squares are actually talking about squares. So x squared is really talking about some kind of a square. Let's say I'm using all the little blocks in here, and there are 16 of them. So x squared is 16 is saying I'm looking at a square. What would the square root be? So we can understand now that the square root symbol is asking you to consider a square that has 16 blocks. If we root it or organize it, chop it into even amounts, which they're drawn here, we know it's going to be a 4 by 4, a 4 by 4 row. Now we know this because number one, a square has equal sides or congruent sides. And we know 4 times 4 is 16. So that's why we would say the square root of 16 is 4. So what we're saying is, we'll use another number. When you have 25 little boxes, the square root means what's the root of one side? So when you have 25 little blocks, the root of one side is 5. So that's why the square root of 25 is 5. And we break it into 5 times 5, and we use one of those numbers because we're talking about the two sides of a square. 5 times 5. Well, when I ask what the square root is, I'm asking what's the root of one of the sides. So the same would work with cubes, cubed roots as well. You're saying I have a cube, and I want to find one of the sides. And it works in the same way. So let's look at squares. Here's a square, here's a square, here's a square. And pretend they're the same size. And then I have one left over. And I have 48, 49. Let's say 49. I think this will work. So what I'm saying here is I have a square. That would be a square, x squared and x squared. This is a little brick, so it'd be like the number 1. So I have 3x squared plus 1 equals 49. So again, I can take away one brick here, but I'd have to take away one there as well and make it 48. So I subtract 1 on both sides. And then I know there's 3 of them, so if I divide by 3, I want to know how much 1 squares, how many bricks we use. So we're going to get 16. And again, in normal algebra, we would square root it and say, well, what is the root of one side when the square is 16? So you'd have 16 little cubes in here, 16, and I want to know what the sides are. Well, it's a 4 by 4. 4 times 4 makes 16, so we know it's 4. Now in regular math, in algebra, we would say positive or negative, because negative 4 times negative 4 is also 16. But in real applications for bricks, there's no such thing as a negative brick. So we would leave it as just 4. So what are we talking about even when we're giving imperfect squares? So what is a perfect square? Well, a perfect square is a number of rows and columns that make a square perfectly. So think of a pyramid. We have a pyramid we're building, and the base or the bottom of it is a square. So if we think of it and we section it off in rows, here's a row, 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 here's a row. When we're looking down on that shape, we're going to have the very top is going to be a 1 by 1 square. And we're going to have a bigger square, a bigger square. So these are the layers of the pyramid. And when we stack them on top of each other, they'll look like a three-dimensional pyramid. So if you have little algebra tiles or even little squares, you can have someone play with these who's never done squares and square roots and understand how to make a perfect square, because you could give them one tile and they could see it's a perfect square. 1. Well, there's 1 row and 1 column, so there's 1 total. And you might give them, they might have 2, and then they'll try, no, it's not a square. 3, no, it's not a square. 4, oh, now it's this perfect square, 2 by 2. So a 2 by 2 is going to give us 4. We can keep going by whole numbers. A row with 3 by 3 is going to give us 9. A 4 by 4 will give us 16. A 5 by 5 square will give us 25. So these are perfect squares because we have the right amount of whole bricks. We don't have to chop the bricks. And I'll explain what I mean by that in a moment. So that's how we get, 1 squared, 2 squared, 3 squared, 4 squared, and we can continue that pattern. and we're just looking at an actual square shape, how many bricks would be on the inside of it? So what is an imperfect square? An imperfect square is when the square doesn't have a regular amount of bricks with whole numbers. So let's say I have 5 bricks. Well, we know that 4 will give us a 2 by 2, and that we can put those together to make a square, but we have 1 left over. What would we need to do? So what we're asking here is, what is the square root of 5? 5 bricks, we want to make it into a square. Well, we could line the 4 squares up and make a 2 by 2. But I have this one left over here. So what I'm going to need to do is take the one that's left over and do what this symbol sort of represents, is chop it up into even amounts. And I'm going to chop it into several pieces, and I'll put a piece here, put a piece here, put a piece here, put a piece here, and I'll also need a piece right there. Now it's still an even perfect square. Now the point of this is I had to chop up the little square that's red into little pieces. So I know that I have 2 whole pieces, and I have some little amount that I had to chop my extra square into. So we get that number, and we can use a calculator to find it. It would be, oops, we'd have to get 1. Square root of 5, so it's 2.23. So you have your 2 whole numbers, plus you have 0.2 here, 0.2 here, 0.2 here, 0.2 here, and this little amount. So an imperfect square simply means that we have to take the leftover bricks and chop them into small pieces. So let's say we have a 3 by 3. And I have 1 more brick left over. So there's 10 bricks. Well, what's the square root of 10? Well, we know it's going to need to be chopped into smaller pieces now. And it might be somewhere around 3.1. Let's see. .16. So I have 3 whole ones, and then I have 0.16 on each side. And here's the thing about these numbers. If we're honest about them, we see that they're continuing forever. So 3.16227766016837 and it just keeps going. So square roots have this infinite decimal. So if you're actually building these, you probably can never get them right and get the exact same amount for each of them. So square roots and infinite squares are interesting, or infinite numbers are interesting, because we can't really find the end of this number. However, we can draw some of these things. So for example, when you take a square, we learned about 45, 45, 90 triangles. When you take a 1 by 1 square, the hypotenuse, or the diagonal here, is going to be the square root of 2. So even though the square root of 2 is a decimal that goes forever, 1.4142, and it just keeps going, we couldn't calculate that number perfectly. It'll just keep going. And it was really hard to get accurate and to get it to the number of places the calculator can. And so we can get very, very, very accurate in cutting these, but technically it's a number that's infinite. Nevertheless, we could still draw it. So even though it's an infinite number and we couldn't even finish this decimal, we could draw it. So again, it's interesting that sometimes you could draw something that you can't really explain, because you'd have to be able to get to infinity to finish this number, which is technically impossible. So it's a little bit interesting when we begin to look at algebra visually. Let's say we have a square. You have 2 rows, and you have some extra bricks. What we're really describing here are actual shapes and things that you would use to build. And so this would say we have x squared plus we have 2 rows of x plus we have 3 bricks left over. And we could say that adds up to so many bricks, 100. And we could use different mathematical ways to solve this and find what actual amount of bricks we would have in the square, in the rows, and we know there's 3 left over. So it's a lot of information, but if we have already covered algebra and we're finishing geometry, I just wanted us to understand that these shapes and visual things are real things that you can use to build. And the idea of a square and a square root are really talking about an actual shape of a square and the root of each side. Same with the cube. How many little cubes would fit inside of this space? Algebra itself, it's not some made-up thing so much as trying to explain what we have, and again, it saves us so much time and energy than if we were to have to count everything. You imagine you tried to count the number of dollars in your bank account, but you could only use your fingers. There are systems and ways you could eventually figure it out, but it would be very, very complicated. And this algebra allows us to deal with a lot of complicated shapes and information without actually having to look at them, without having to draw each of them. And it lets you really go far in what you can understand both about a problem and what you can predict.